Mid-February 1943, Sidi Bouzid, Mamoun Ahmad. Mid-February 1943, Sidi Bouzid, Tunisia. The captured M4A1 Sherman tank rolled to a stop in the desert sand, its American star still visible under the quickly painted German cross. Officers from Heavy Panzer Battalion 501 gathered around this prize, notebooks already in hand. This single American tank, captured intact and working during the Battle of Sidboid, would cause a crisis of confidence among German engineers that would echo through their tank development programs for the rest of the war. The mathematics of armored warfare were about to be rewritten, not by better firepower or thicker armor, but by something the Germans had never focused on: automotive excellence that just refused to break. The tank had the name War Daddy 2 painted on its hull, serial number USA 3067641, built by Lemmer Locomotive Works, belonging to Company G of the 1st Armored Regiment, 1st Armored Division. Personnel from a German reconnaissance unit drove this Sherman 350 kilometers across North African land to the port of Sfax, a trip of 4.5 days. Every kilometer showed something that went against German ideas about American industrial strength. The engine never overheated, the transmission never failed. The final drives kept working well. German tank crews, used to frequent mechanical stops even on short moves, watched with growing worry as this enemy tank just kept working without complaint through land and conditions that would have broken their own machines. At the port, War Daddy 2 was loaded onto a cargo ship heading to Germany. The Army Weapons Office had given clear orders. This tank must reach the testing site at Kummersdorf fully working. German intelligence had gotten some reports about American tank production, but seeing the real tank made those numbers real in a way paper never could. The Sherman showed mass production on a scale Germany could not match, built with automotive engineering that Germany had not mastered. As the ship moved north across the Mediterranean, Wehrmacht engineers got ready with testing plans that would show truths they had not wanted to see about their own limits and American abilities. Spring 1943, Kummersdorf, Proving Ground. Brandenburg, Germany, War Daddy 2 rolled off the transport rail car, carrying the designation for Zugfahrts 259N, German license plate WH058941. Test engineers had already stenciled armor thickness measurements and angles across every surface of the tank, marking it with exact notes for their full evaluation program. The German Army Proving Ground at Kummersdorf, 25 kilometers south of Berlin, was the main testing place for both German and captured Allied machines. Here, careful engineers measured, tested, and studied everything from track tension to transmission efficiency, writing down their findings in very detailed technical reports. The Sherman was about to go through the most complete automotive check German engineering could imagine. German test engineers did the first inspection with teams of specialists from many technical areas. They photographed every part from dozens of angles, measured every clearance with precise tools, and wrote down construction methods that seemed impossibly simple compared to German ways. The transmission got immediate attention from powertrain experts. Where German tanks used straight-cut gears needing exact tolerances and frequent maintenance, the Sherman used herringbone-cut gears that spread stress across many teeth at once. This design, standard in American car making since the 1930s, gave amazing durability with very little need for precise work. German engineers thought herringbone gears were too hard to mass-produce with their industry and trained workers. But Americans were making them by the thousands. Testing started with basic automotive trials meant to stress every mechanical system under controlled conditions. Engineers drove War Daddy 2 through obstacle courses made to copy battlefield situations, measuring fuel use, checking engine temperatures, and recording transmission behavior under different loads and terrains. After each trial, they took parts apart to check wear patterns, looking for stress signs, poor lubrication, or design problems. The results went against everything German tank rules had taught about the trade-offs between performance and reliability. The Sherman did well in every category and shined in the one thing German tanks always failed at: operational endurance without maintenance help. The powertrain check showed design differences that explained a lot about American versus German approaches. The Sherman transmission had 5 forward speeds plus 1 reverse, with synchronization in gears 2 through 5 that removed the need for double clutching during normal driving. This made the tank almost as easy to drive as regular cars, needing very little special training for drivers. German tankers, in comparison, spent a lot of time learning tricky double-clutching methods and careful throttle control to avoid breaking their transmissions. The Sherman's design assumed ordinary soldiers with basic car knowledge would drive these tanks, while German designs assumed highly trained specialists would always be there. The Continental R975 radial engine in this Sherman showed amazing tolerance for different operating conditions. Engineers noticed that the engine kept working well across temperatures that would have made German engines overheat or lose power. The cooling system, though simple, worked very well. The air filter handled desert sand without the frequent clogging that caused problems for German tanks in North Africa. Every system showed a design that focused on practical use instead of theoretical perfection. June 6 and 7, 1943. Hillis-Lehen Artillery Range. Reich's Minister Albert Schar came to lead a major armament conference with leaders from the arms industry and senior Wehrmacht officers. The demonstration program included hill climbing tests comparing German and captured Allied tanks. War Daddy 2 sat next to the newest German designs, including a Panther ASEF-DM tank straight from production and a Ferdinand tank destroyer showing Germany's most advanced armored technology. Schar, in charge of German armament production and responsible to Hitler for results, needed to see what American industry could make and how German tanks compared to enemy machines. The test would give answers neither Schar nor German tank designers wanted to face. The Sherman climbed the test hill smoothly. Its manual transmission, with 5 forward gears, synchronized from 2nd through 5th, shifted without any problems. Its engine kept giving steady power during the whole climb. The driver controlled the tank confidently, showing the easy operation that would become a Sherman trademark. The Panther, with its stronger 700 horsepower Maybach HEL 230 engine, followed and managed to match the Sherman's climb, but just barely and with much more effort. The Ferdinand, very heavy at 65 tons and technically advanced with its electric transmission, stalled partway up the slope. Speer watched as recovery crews struggled to restart the vehicle, the embarrassing failure happening in front of dozens of senior officers and industrial leaders. In his memoirs years later, Speer would write about Sherman abilities he saw during his inspection tour of Italy in October 1944. He noticed that reports on the cross-country mobility of the Sherman had been very positive. With the tank climbing mountains, German tank experts thought tanks could not climb. He said this was because the Sherman had a very powerful engine for its weight, giving it cross-country mobility on flat land that was clearly better than German tanks. The 26th Panzer Division had specifically reported this advantage. These notes from Germany's armaments minister carried a lot of weight in Wehrmacht circles. The public report appeared in Das Reich newspaper on June 27, 1943. The article described the Sherman as one of the special achievements of North American labs and called it a very praiseworthy product of the North American steel industry. The article said the first things to notice were serial construction and meeting the almost bold standards of the North American car industry. It mentioned the gyro-stabilized gun as the first attempt of its kind anywhere, recognizing American innovation in this area. These public statements were carefully worded for propaganda so they would not seem defeatist, but they hid the private alarms spreading through German engineering departments. American tanks were not just okay, they were actually better built for long field operations. Back at Kumdorf, systematic testing went on through summer and into autumn of 1943. Engineers measured the Sherman's operational range, doing long trials that pushed the tank to its limits. They recorded operational ranges over 2,000 kilometers before needing major maintenance, about 4 times what early model Panthers could do in the field. They measured transmission efficiency higher than any German tank, with power losses in the drivetrain much lower than similar German systems. They studied the synchronized manual transmission that made gear changing smooth and easy, needing neither double clutching nor careful rev matching that German tanks required. The final drives gave another surprise that challenged German engineering ideas. German Panther tanks used final drive systems from the Tiger design, a setup that often failed under stress. The design used straight-cut gears in housings that could not handle the loads of the 45-ton tank German mechanics in North Africa and the Eastern Front had reported final drive breakdowns, forcing Panthers to be left behind after relatively short moves, sometimes less than 100 kilometers. The Sherman's final drives, built using the same herringbone gear ideas as the transmission, rarely failed even under long combat conditions that would destroy German parts. Restoration projects decades later found Sherman final drives that needed no mechanical repair after years of storage, showing design margins that went far beyond immediate needs. By late 1943, Kumdorf had collected enough data to make detailed internal reports that circulated through Wehrmacht technical branches. These documents, meant for senior Wehrmacht officers and armaments ministry officials, showed a sobering picture of comparative abilities. The Sherman showed American automotive engineering maturity that Germany completely lacked despite its theoretical knowledge and science skills. Mass production methods allowed tolerances that would be seen as sloppy in German precision work, yet made more reliable vehicles that work better in the field. Interchangeable parts meant field repairs could be done with basic tools and little special training. While German vehicles needed factory-level precision and special equipment for many repairs, the whole design focused on keeping vehicles running instead of reaching theoretical performance numbers that looked good on paper but could not be kept in combat. Internal German engineering reports noted American industrial advantages that went beyond simple production numbers. American automotive engineering reflected decades of civilian industry experience that Germany had never reached at the same scale. Before the war, the United States had widespread car ownership with vehicles common among ordinary citizens. Of all income levels, Germany had much less civilian car experience, with cars staying luxury items for the wealthy and party leaders. The Volkswagen program, promised to German workers since 1934, had produced fewer than 1,000 civilian vehicles by 1939. This big difference in car industry experience directly affected tank design ideas. Americans built tanks that mechanics with regular car training could maintain using skills they already had. Germans built tanks that needed specialist training and constant expert attention from people with years of specific military technical education. The comparison with German tank reliability became impossible to ignore. As field reports came in through late 1943 and early 1944, Panther tanks needed strict operational limits to prevent mechanical failures that would leave them stranded. Drivers got clear instructions not to change gears too often because too much shifting broke the transmission. Third gear especially broke often enough that field manuals warned not to use it unless really necessary. Panthers could not turn while going backward because this would destroy the transmission. Pivot turns were only possible when ground resistance was the same on both tracks, severely limiting tactical flexibility. Foreign objects getting into the running gear could jam the drive sprocket, needing hours of maintenance to fix. These problems existed even though Panthers were built in special tank factories by skilled workers using the best materials Germany could provide. The Sherman, by contrast, was designed by car engineers at General Motors, Ford, and Chrysler using mass production methods they had built over decades of civilian car making. The tank used commercial automotive parts wherever possible, using existing supply chains and manufacturing experience. The transmission came from many makers, including Caterpillar Tractor, Buick, and Ford Motor Company, all built to the same specifications with fully interchangeable parts that could be mixed freely without adjustment. This standard way of doing things, common in American car industry, stayed mostly theoretical in German tank production, where each maker added small changes that stopped real parts interchangeability. More captured, Shermans arrived at Kumdorf during 1943 and 1944, including tanks taken from British units in Italy and Soviet forces on the Eastern Front. Each captured tank went through similar testing, making a full database of American tank abilities across different models and production times. The British had upgraded some Shermans with their 17-pounder anti-tank gun, making the Firefly variant that fixed the Sherman's main weakness in firepower. German engineers studied these modified tanks closely, noticing how the Sherman's big turret ring fit the much larger gun with very little change. The Firefly showed the original design had room for upgrades that German engineers had not thought about when designing their tanks. The Panther rushed into production to fight. Soviet T-34 tanks had no way to upgrade its guns without totally redesigning the turret and tank. The automotive testing program grew to include reliability trials made to copy real combat. Engineers drove Shermans through hundreds of kilometers of cross-country travel, recording every mechanical problem, maintenance need, and component failure. They compared these results with field reports from Panther and Tiger units working on the Eastern and Italian fronts. The numbers told a clear story about reliability. Panther operational readiness averaged below 40% for most of 1943, with some units reporting disaster rates as low as 20 to 25%. Individual Panther battalions noted times when fewer than 1 in 5 tanks could actually fight. By comparison, Sherman tanks kept much higher operational availability in all theaters. Specific data from German field reports showed Panther reliability problems in great detail. In July 1943, during Operation Citadel, at Kursk, Panthers reached only 16% operational readinesses, with mechanical failures taking out more tanks than enemy attacks. By December 1943, readiness was only 37%. February 1944 reports showed 37% operational. AD 1944 reached 50% operational. May 1944 finally reached 78%. These numbers showed the percent of Panthers that could really fight on any day, with the rest broken down, waiting for parts, or being fixed. The trend showed slow improvement as design flaws were fixed. But even the best Panther readiness never matched what Sherman's did from the start. By December 1943, the pattern was clear to any objective observer looking at the data. Engine life for the Sherman diesel version went over 3,000 kilometers with proper maintenance. Panther engine life barely hit 1,000 kilometers, even after fixes for early problems. German reports from March 1944 said improved Panther engines lasted 700 to 1,000 kilometers, presented as a success. This improvement only brought Panther engines to about one-third of Sherman diesel ability. Sherman transmissions needed very little maintenance between overhauls with synchronized gears that made driver mistakes less likely to cause damage. Panther transmissions needed constant care and frequent repairs, with third gear failing so often that drivers learned to go from second to fourth gear to avoid the bad ratio. Sherman final drives worked reliably in conditions that normally destroyed Panther final drives within 100 to 200 kilometers of use. Field reports from German units using captured Shermans backed up the Komdorf testing data with real-world experience. German mechanized units, desperate for reliable tanks as their own tank forces fell apart eagerly, used any captured American tanks they could get intact. Unlike Soviet T-34 tanks, which Germans changed a lot before use, Shermans went into German service without changes. They did not need modification because they worked right as designed with no major problems. German tank crews who had many mechanical failures in their own vehicles found the Sherman's reliability amazing and often wrote about it in letters and reports. Reports from Panzer regiments said Sherman drivers could focus on tactics and fighting, while Panther and Tiger crews always worried about getting to the battlefield without breaking down or finishing missions before mechanical failure stopped them. The 10th SS Panzer Division captured 12 M4A3 Shermans at Hellesheim in January 1945 during Operation Nordwind. These tanks had belonged to the American 43rd Tank Battalion and were captured intact when their crews abandoned them during the German attack. The 12 Shermans became the 13th Company of the 10th SS Panzer Regiment and fought in combat for the rest of the war. These tanks worked as scouting vehicles and mobile reserves jobs that needed constant movement, without maintenance stops and reliable mechanical performance. German commanders saw what Kummersdorf testing had proven years before American tanks could be counted on to work when needed. This dependability, more than firepower or armor, made them useful in the last months of the war. A Sherman arriving at the battlefield with a working gun was far more valuable than a Panther with stronger firepower, broken down 20 kilometers behind the lines. January 1944 brought bigger testing programs as Wehrmacht forces retreated across multiple fronts and more captured tanks reached Kummersdorf. Engineers checked the M4A1 with the Continental R975 radial engine, noting its features and comparing it to other models. They tested the M4A2 with twin General Motors 6046 diesel engines, noting its better fuel efficiency and different operating traits. They checked the M4A3 with the Ford GAV8 gasoline engine, which American crews thought was the best Sherman power plant. Every variant showed the same basic trait: excellent automotive reliability coming from strong engineering and good manufacturing. The consistency across models impressed German engineers, who were used to big quality differences between different makers. making supposedly identical vehicles. The diesel-powered M4A2 especially impressed German engineers who checked it at Kumdorf. Soviet forces got 4,100 of these tanks through Lend-Lease, and many ended up in German hands during retreats on the Eastern Front. The twin GM6046 diesel engine gave performance like any Sherman variant, while using much less fuel than gasoline engines. A key advantage as German fuel supplies ran low, German designers had tried diesel tank engines but gave up because of manufacturing problems and complex fuel injection systems. American industry made diesel Shermans along with gasoline versions without stopping production, showing manufacturing skill and technology that German industry never reached during the war. March 1944 brought reports from General Heinz Guderian, Inspector General of Panzer Troops, saying in official reports that Panther reliability had reached what he called acceptable standards. By early 1944, engine life hit 700 to 1,000 kilometers, and final drive problems were mostly fixed with design changes and better manufacturing. This improvement, presented as a big success in German military reports, only brought Panther reliability to the level Sherman had from first production in 1942. The German army celebrated meeting standards that American tanks had exceeded from the start, showing how far behind German armored development had fallen. The comparison got worse as German tank production struggled with growing resource shortages and Allied bombing. Allied raids targeted key points in Panther and Tiger production, with growing success. The Maybach engine plant in Friedrichshafen was badly damaged by Royal Air Force Bomber Command on the night of April 27 to 28, 1944. The raid used 322 planes and is called an Imperial War Museum archives, the most damaging raid on German tank production in the whole war. The attack also destroyed the ZF gearbox factory next to the engine plant. Tank engine and transmission production stopped completely for 6 months, when production finally started again in November. 1944, quality control had dropped a lot. Slave labor increasingly used in German tank factories as German workers were drafted into military service, caused deliberate sabotage. Cigarette filters were stuck in oil passages. Gaskets were put in wrong. Components were put together without proper clearances. These problems never affected Sherman production safely made in American factories, far from any combat zone and run by motivated workers, earning good wages under decent conditions. The main difference between American and German tank production was not engineering knowledge, but industrial ability and basic design ideas. German engineers knew automotive principles as well as American engineers, having lots of theoretical knowledge and science skills. They just never used those principles consistently in tank design, instead focusing on other things. German tanks focused on performance that looked good on paper, but had poor reliability in the field. The Panther's strong 75mm KWK 42 gun and thick front armor came at the cost of an overworked powertrain that could not reliably carry the 45-ton tank. The Tiger's powerful abilities needed complex maintenance and frequent repairs by highly trained specialists. These trade-offs might have been okay if German industry could make enough tanks and enough spare parts to keep them running. It could not, especially as Allied bombing grew and raw material shortages got worse. American engineers trained in mass production through decades of civilian industry made tanks that could be built by the tens of thousands and kept running by mechanics with basic training, using skills learned in civilian life. The Sherman powertrain used parts proven in commercial service with design ideas directly from car and truck making. The electrical system had a backup generator that could turn the turret even when the main engine stopped, a feature that seemed like a luxury to German engineers, but was priceless in combat. German tankers could only dream of such conveniences, especially those who saw their turret fail when engines stalled on slopes. These features were not in German technical specs because German designers never thought they were important compared to armor thickness and gunpowder. By spring 1944, Wehrmacht units on all fronts reported more mechanical problems as manufacturing quality fell and spare parts became harder to get. Panthers needed to be moved by rail for trips over 100 kilometers because their final drives could not survive long road marches. Field commands gave clear orders limiting Panther movement to save the tanks for real combat, instead of losing them to mechanical failure on the way. The Berger Panther recovery vehicle, built on a Panther chassis to recover broken Panthers, had the same reliability problems as the tank it was supposed to fix. German commanders faced the harsh reality that mechanical failures destroyed more tanks than enemy attacks. with some units reporting 70% of tank losses came from breakdowns, not combat. Meanwhile, Sherman production kept going in at record rates that German industry could never match. American factories made 49,324 Sherman tanks during the war, more than all German tank production of all types combined. British Commonwealth forces got thousands through Lend-Lease. The Soviet Union got over 4,000 diesel versions. Chinese forces in Burma used Shermans very effectively against Japanese tanks that were worse than both American and German designs. Every battlefield where Shermans fought confirmed what Kummersdorf testing had shown. Properly maintained, Shermans kept working in conditions that would break or destroy German tanks. German tank crews who captured and used Shermans always praised their automotive quality in letters, reports, and post-war interviews. Reports from the Eastern Front said German mechanics found even the complex Chrysler A57 multi-bank engine with its 5 separate engine blocks easier to fix, compared to German tank engines that needed special knowledge and tools. The Ford GAA 5.8, praised by Allied crews for its reliability and power, seemed very dependable to German mechanics used to Maybach engines that needed constant adjustment of valves, ignition timing, and carburetors. The General Motors twin diesel, which the U.S. Army had rejected as less reliable than gasoline engines, and made only for Lend-Lease, far outperformed any diesel engine German industry had made for tanks. The Sherman's large design margins gave another advantage that German engineers came to respect. The basic transmission and final drive parts originally made for the 30-ton M4 with 400 horsepower needed. No big changes to handle the 42-ton M4 A3 E2 jumbo assault tank with much thicker armor. The same parts that powered the normal Sherman successfully handled 650 horsepower from experimental engines without breaking or needing reinforcement. German engineers usually thought such overbuilding was waste extra capacity that raised production cost and used rare materials with no immediate benefit. American engineers knew that these margins gave room for future upgrades and battlefield reliability, making the extra cost worth it over the tank's service life. By summer 1944, German tank commanders facing the Allied invasion at Normandy knew their technical problems went far beyond single tank abilities. American artillery power, devastating close air support, and huge supply capacity combined to beat German forces. No matter the tank specs or skill, but the Sherman's reliability meant American armored units could keep fighting, non-stop, that German Panzer divisions could not match. American tank battalions could attack, fight, pursue, and get ready for the next battle without long maintenance stops. German Panzer divisions had to carefully save their few operational tanks, knowing that every move used up component life and risked breakdown. The difference in operational readiness decided which army could keep pressure and which had to carefully ration its limited combat power. Using captured Shermans in combat gave final proof of American automotive superiority from the German view. The 150th Panzer Brigade made for infiltration missions during the Battle of the Bulge. In December 1944, tried to get captured American tanks to hide their operations. German planners wanted Shermans because of their reliability, but the brigade got only 2 Sherman tanks, and only one worked well enough for operations. The working Sherman never actually fought because massive traffic jams stopped the infiltration mission from reaching its goals. In a mission needing vehicles to function without braking while working behind enemy lines far from help, only American tanks gave real chances of success. German tanks, even when fully working, could not guarantee the steady performance such missions needed. January 23, 1945, brought the final official admission of German automotive failure. A meeting of the Panzer Commission made a report showing catastrophic final drive failures in all German tank types. The document's findings were shocking. Before the 1945 Eastern Offensive, there were 500 broken final drives in the Panzer IV 370 in the Panther and about 100 in the Tiger. Also, about 200 failures were reported in the Hetze tank destroyer based on the Czech 38-ton chassis. General Wolfgang Thomel, General Littmann, and Chief of Staff of the Inspector General of Panzer Troops under Guderian explained the effect clearly. In these conditions, proper use of tanks was simply impossible. Troops lost trust in their tanks and in some cases abandoned whole vehicles just because of final drive problems, afraid they would be stranded and captured. German tanks built to scare with impressive specs failed at the most basic need of armored vehicles. Mechanical reliability enough to reach the battlefield and finish missions. Kumasov testing facility got ready to evacuate in early 1945 as Soviet forces pushed toward Berlin. Engineers hurriedly packed testing data and sent documents to facilities farther west, hoping to save technical knowledge for post-war study. Some captured tanks, including at least 2 Shermans, were pressed into emergency service with combat units desperately defending approaches to Berlin. These vehicles fought alongside German tanks in the last desperate battles, giving one last comparison under real combat conditions. The Shermans kept working until destroyed by enemy fire, or left when fuel ran out. German tanks, including Panthers and the few remaining Tigers, broke down from mechanical failures at rates that shocked even crews used to poor reliability. The story of War Daddy II and the many other Shermans tested at Kumdorf shows one of the biggest industrial differences of World War II. German engineers, working in a system that valued perfect theory over practical use, made tanks that looked good on paper but failed in long field operations. American engineers, using decades of car-making experience for military needs, built tanks that lacked technical complexity in many areas, but worked reliably in conditions that broke German tanks. In armored fighting, like most military actions, the weapon that works when needed beats the weapon that might be better on paper if it could get to the battlefield and finish its mission. After the war, American and British intelligence studies confirmed what German testing at Kumtov had shown. Careful checks of destroyed German tanks found mechanical failures as common as combat damage as causes of loss. Final drives broken from stress transmissions, seized from bad lubrication or operator mistakes, engines burned out from overheating or low oil. German focus on single tank superiority and impressive specs had blinded them to the real need for reliability and maintainability. They built tanks no ordinary mechanic could fix without lots of special training, powered by engines that needed constant expert care from skilled technicians, and supported by supply systems that collapsed under the strain of giving many unique parts to scattered units. Lessons learned from testing at Kumtov directly influenced German tank design thinking in post-war West Germany. When the Federal Republic started making the Leopard 1 main battle tank in the 1950s, designers focused on reliability and maintainability over just performance specs. They studied American car engineering ideas and deliberately used them in military vehicles. The Leopard 1 tank used many design ideas that made the Sherman successful. Strong powertrain with big design margins, easy maintenance needing few special tools, standardized parts and letting quick field repairs and room for future upgrades without redesign. The Leopard 1 became one of the most successful tank designs of the Cold War, serving with many armies and staying in production for decades. The captured Shermans at Kummersdorf, including War Daddy II with its name still on the hull, were more than enemy tanks brought home for study. They were proof that industrial skill and good engineering based on practical experience mattered more than technical innovation done without thinking about real manufacturing. German tank industrial superiority, shown as mechanical reliability, steady availability, and easy maintenance. German engineers at Kumdorf understood this by mid-1943 from their detailed testing. They wrote long reports documenting what they found. They tested the proof over and over with scientific care. They reached the right conclusions about American advantages, but knowing a problem and fixing it are very different. German industry did not have the ability to rebuild production for reliability while fighting a losing war on many fronts against enemies with better resources. American industry had built reliability into its civilian car industry over decades of competition and just applied those mature ideas to military production with great success. War Daddy II, that single Sherman tank captured in Tunisia and tested fully at Kumdorf for months, told the whole story through its mechanical reliability and steady performance. Every kilometer it drove without braking showed that German tank design had gone the wrong way by focusing on specs over reliability. Every test showing American car skills proved that real industrial experience mattered more than theory. Every comparison of Sherman and German tank reliability proved Americans had solved problems German engineers did not even know they needed to solve. The tank itself was ordinary in many ways, just one of 49,000 made. What it showed was crushing to German confidence, proof that Germany had already lost the industrial war, even while fighting continued, and that American production could not be matched no matter how good German engineering or tactics were.